Hey, this is Chris Burke here. I'm just testing out our lightboard system in the One Button Studio over in Henzlik Hall. And I thought I'd just put together a really quick lecture on Quicksort, since that's what we're doing in CS2 right now. Hopefully you've seen Quicksort before. It dates back to the 60s. It's an old sorting algorithm, but it is also very quick in practice, giving it its name. It's also has a very good theoretical bound of average case complexity and best case complexity of order n log n. So it's very competitive with other algorithms like merge sort, heap sort, and stuff like that. So just to give you an idea of how Quicksort works, I'm going to go ahead and set up an array here. Right? We won't worry about generalizing this to sorting elements of any type. Instead, we'll go ahead and simply just sort an array of integers. And I want to make it large enough that it is non-trivial. Right? And I'll go ahead and draw this as an array. Okay. So remember that Quicksort is a divide and conquer algorithm, meaning that it is going to divide the array into roughly, hopefully, 2 equal lengths, and then sort one, we call them partitions, and it's going to sort one partition and then recursively, and then it's going to sort the other partition recursively. The key idea here, though, is that the way that it partitions that and splits it up into 2 is by choosing a pivot element. There are lots of ways that you can choose a pivot element, but we're going to simply just choose the first element, right, that we see. Again, there are lots of different strategies that you can use. Some of them are better than this in practice. Some of them ideally you should be choosing the median, but if you knew where the median was, then you might already have it sorted. Oftentimes finding the median involves sorting it and then choosing the middle element. So putting the cart before the horse. So once we've got this pivot element, it's called a pivot element because what we're going to do is we're going to look at the rest of these elements, and then we're going to take everything that's smaller, 4, 9, 4, right, and 0 and 2, and we're going to put them on this side of the array. Then everything that's larger, 101, in this case there's only one thing here. So let me go ahead and actually modify this to be 44, just so that it's a little bit more interesting. You know, these two will be on the other side, the right side. We're going to be sorting in non-decreasing order, in other words, ascending order. So the way that we're going to do that is we establish two, I don't want to call them pointers, they're index variables. We'll go ahead and establish two variables here. I is going to start here, and j is going to start here. Now what we're going to do is we're going to start with I, and we're going to move this over and over and over until we find something that is on the wrong side of the array. 102, right? Eventually we're going to be putting 42 somewhere in the middle here, and everything over here is going to be less than it, and everything over here is going to be greater than it, and then we'll recurse. But we need to find something that's on the wrong side, 102. It needs to be on that side. And then we're going to start over here and find something that's on the wrong side. We find that immediately. 0 is on the wrong side because 0 is less than the pivot element 42. So once we've found these two things, if they're both on the wrong side, then all we need to do is swap them. Right? So let me go ahead and do that. We make a comparison I here. I is the element is 4. It's less than 42, so we move on to the next element. 9 is less than 42, so we move on to the next element. Right? 4 is less than 42, so we move on to the next element. And at this point we stop because 101 is greater than 42, so it's on the wrong side. We need to put it over here. We do the same basic loop. It's going to be a while loop when we write the pseudocode. It starts over here for j, and then it's going to move over here until it finds something that's less, but immediately we found something that's less. So I and j, these two things are on the wrong side, so we're going to end up swapping them. Right? And when I do that, I have 0 here and 102 over here. Right? Just making sure that I got that right. Yep. Okay. I and j didn't change. They're still pointing, or referring, you should say, to these two elements, 0 and 102. So we continue. I moves over here. 44 is greater than 42, so it's on the wrong side, right? So immediately we stop. This thing needs to be moved over that direction. And then J we move down. And likewise, in the very first iteration here, we see that, oh, well, 2 is on the wrong side. We need to swap these two things. Right? When we do that, we get 2 right here. And we had 44 over there, so now it's on the correct side. Okay? So we're done with the swapping. Now we repeat those 2 loops again. We've got a loop over here for I, we've got a loop over here for J, and when we stop, or when do we stop all these loops? It's when I and J meet in the middle, right? Because now everything over here is less than the pivot, everything over here is greater than the pivot, so we've zeroed in and they've met. In other words, I is equal to J. So let's go ahead and continue simulating here. Again, we start with I. It moves over here. I is, now it's referring to 12. 12 is less than 42, so it's less than the pivot. It's on the correct side. So we increment I again. And at this point, we see, well, it doesn't matter that it's looking at 42, and 42 is on the on the correct side, right, over here. But I and J are now pointing or referring to the same element. So at this point, we stop, right? And if we look at this array, right, where should the pivot element be? It should be right here, between 12 and 42. Right? So we need to make an additional check here. I need to determine whether or not this thing needs to be exchanged with the pivot element, or this thing needs to be exchanged with the pivot element. All right, if I exchange this 44 over here and 42 over here, then 44 would be on the wrong side over here. It would be 44 is greater than 42, but it would be on the left side. So we don't want to do that. Instead, we look at the one previous element here and say, oh, well, 12 is less than 42. Otherwise, we would have never gotten over here. So that's what we need to exchange. We'll end up swapping the pivot element and the one previous to I and J. Right? So in other words, we do have to do a comparison over here to determine whether or not it's this element that we need to exchange with the pivot element or the one previous to the I and J. So let me go ahead and put over here. It was, now I forgot what it was, sorry. Two. I think it was 2. Or sorry, it was 12, right? Yeah, sorry. It was 12. Okay? So there, now we've swapped it. So I'm going to go ahead and get rid of all of this and make an observation here that this was our pivot element, right? Everything over here is less than the pivot element. Everything over here is greater than the pivot element. So the pivot element is where it needs to be, right? If we put 42 anywhere else, then ultimately that's not going to be a sorted list or a sorted array. So what we need to do is now we need to recurse on this right partition. And we need to recurse on this left partition. Right? We're going to sort this list, and then we're going to sort this list. Now in this particular example, we've got 1, 2, 3, 4, 5, 6 elements over here and only 2 elements over here, so it's not an even split. Ideally, it would be nice to have an even split because then we get the best case running time for Quicksort when we analyze it, but that's not always going to be the case, like it is here. Just because of our pivot choice element. That's going to influence whether or not we have an even split or a bad split where everything's over here and then there's nothing over here, or everything's over here and there's only one element over here. But it's not always going to be that way. All right? So let's just go ahead and recurse on this left partition here, because as you can observe right here, this is already sorted. So you would end up looking at this as a pivot element, seeing that this is on the correct side, and then you'd be done. Right? So let me go ahead and get rid of this, and let's look at one more example, the left partition here. Okay. There we go. So again, taking the same strategy, this will be our pivot element. And then we've got I and j. And this is less than 12, 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 this is less than 12. So as you can see, on our very first loop here, we end up with a very bad partitioning, because what's going to end up happening is we look, should this be exchanged with the pivot element, or should this be exchanged with the pivot element? It ends up being this one, and we put 2 down here. And now our left partition is this thing, and what is our right partition? It's empty. So that's like the worst case scenario for quicksort, because if you do that, then it's basically no better than insertion sort, right? Or it's no better than selection sort. So it's not always going to be ideal, but it's not always going to be the worst case scenario here, okay? But that's the idea. We ended up putting it over here. We recurse on this. We recurse on an empty list, which ends up doing nothing, okay? Now, what I want to do is I want to write some pseudocode for this. But before we start writing the pseudocode, let's generalize those 2 examples that we just had. So at some point in the algorithm, I've recursed, and I've got a subsection of the array, right? And I don't know what the elements are, but I've got an L and an R, right? I want to sort this subsection of the array. There might be other things over here, there might be other things over here, but what I'm concerned about is the subarray starting at L and going up to R, okay? So the idea here is that I'm just going to go ahead and choose this as my pivot element. Pivot. Right. Then I'm going to initialize I and j. Oops. There we go. I'm going to initialize 2 variables, I and j, and I'm going to move I over as long as the element at this index, a sub I, is less than, or equal to if you want to, less than or equal to the pivot element, so in other words, a sub L. Right? So in other words, while this is true, then increment I. That's how I'm going to move my I over to get an element that's on the wrong side. Likewise, I'm going to look at this element over here, and while a sub j is greater than or equal to, it doesn't matter, a sub L, then I will decrement my j. And that will get my I over to something that's on the wrong side, and I'll get my j over to something that's on the wrong side. After that's all done, I can swap them. Right? So now let's back up here. The pivot element choice up here, well, I wrote it as a sub L and a sub L here, but of course you could go into a pivot to drive home the point in your pseudocode here that you're choosing the first element over here as your pivot element. And then you can make a comparison here with a sub L. Instead of a sub L, you can go with a pivot. And you can go with equals down here, it really doesn't matter. But that's a small loop. Those are the 2 inner for loops that will allow me to find an element that's on the wrong side, find an element that's on the wrong side, and then exchange them. But that needs to continue. Remember on that first example that we did that twice before we actually recursed. So in other words, this entire thing needs to be inside another while loop. Right? Now, let me give myself some more room here. Right? What's our condition for when we stop? Remember, we stopped in the examples when I and j met. So I starts out strictly less than j. So while that's still true, we're going to go ahead and continue to move I over, to move j over, and then swap. Move I over, j over, and then swap. So while I is strictly less than j, we'll go ahead and continue this, okay? Now, this is pseudocode, so maybe this is enough, but you also need to be careful because remember on that example that we just did, immediately J never went over, right? And so you have to be careful, because you could have a loop where they meet, but I'm still in this loop, or I'm still in this loop, or something like that. They've met, and then I goes beyond J, or J goes beyond I. So you need to make sure that that doesn't happen in one of these for loops. And in other words, you want to break out of this. So you could put in a statement here that said, well, if I and J have met, then go ahead and break out of this loop. I'm just going to go ahead and put in a condition here, and I is less than J. And I is less than J for both of these. All right? That ensures that if I has been moved over to J, then when I get to this second while loop here, that it won't even execute. J will never decrement and go beyond I, because if they're already equal, then this condition will fail and you'll go on. So that's the basic loop to partition these things up. We still have to take care of what you do at the end. Remember, this just took care of putting everything onto the correct side. We still need to take care of this pivot element. The pivot element needs to go wherever I and J meet at the end, right? Once they've met, then we either need to put it here, or we need to put it here. So which direction do we do that in? Okay? So I'm going to go ahead and move over here, so that we can continue, but otherwise it'll be continued over here. It's all part of the same algorithm here. So the condition I check is, this is a sub I, which is equal to a sub j, because I and j are the same thing. This is a sub I minus 1, right? The one right previous to it. So what we need to do is we need to take this pivot element and say that, well, if this element is less than the pivot element, then it's okay to go ahead and take it and put it over here, because it would be on the correct side, and so that we can put the pivot element right here. So if a sub I is less than or equal to the pivot element, then we can swap a sub I and the pivot. Right? Else, and I'll go ahead and put the condition in here, even though it's not necessary. If a sub I is greater than the pivot, then we need to put it over here with a sub I minus 1. So swap a sub I and a sub I minus 1. Okay? Now I've left some room here, because we're also going to do some extra work. This is actually going to be a subroutine called partition. Given an array A and L and R, then it's going to go ahead and partition everything around that pivot element and place the pivot element where it needs to be. Okay, oops. Mistake here. You're exchanging the pivot element, sorry. There we go. So again, you place the pivot element where it needs to be. Either you've exchanged it with a sub I, or you've exchanged it in the second case here with a sub I minus 1. But this is a subroutine that's going to be called in the larger routine, that once we've done that, we need to recurse on this side and we need to recurse on this side. Meaning that if you swapped it here and this is the pivot element, or if you swapped it here to here and this is your pivot element, you need to communicate that back up to the calling function, so that the calling function knows to recurse on this stuff or this stuff, and then consequently this stuff, or it's going to be this stuff or everything over here. Right? So what we're going to do is we're going to output the index at which you swapped for the pivot. So in this case, it's going to be I, because you swapped it here. That's your pivot element. That's the index that you need to work off of and go on this one and this, and this one. Otherwise, it's going to be I minus 1, because you exchanged it with I minus 1. Okay? So there's our pseudocode for the partitioning part. Now let me go ahead and erase this, and then I'll show you the main algorithm that uses this. Okay, so let's write so let's go ahead and write the pseudocode for the main quicksort algorithm here. The input will, of course, be a collection. of elements, and our output will be A sorted. Okay? This is going to be a recursion. This is going to be a recursive algorithm. So remember that we had that L and the R index. So we're also going to need that, L and R. Again, if you're going to call this from, to start this all off, L is going to be 1 and R is going to be n because you want to sort the entire collection. But in the recursion, at some point you're looking at only a small part of that array, and so you're only looking at a part of it from L up to index R. First of all, we need our stopping condition. So if L and R are not equal, right? They've not met, remember? Then then we need to sort it. If it's 2 elements or more, 2 elements, 3 elements, 4 elements, 5 elements, whatever, we need to continue sorting that. But if they've met, then that means that the array is the subarray that we're considering is only of size 1, which by definition is sorted, so we don't need to do anything. Likewise, if they've crossed, then that's an array of size negative something, right? Then we don't need to do anything there. So all I need to do for my stopping condition, my base case in the recursion, is to check to see if L is strictly less than R. If they're equal or they've gone past each other, then we don't need to do anything. We can immediately stop this algorithm. Otherwise, what we're going to do is we're going to call that partitioning subroutine that we just developed, which will partition the subarray from L up to R around this pivot element. And this is actually returning not the pivot element itself, but the pivot element index, right? So P is the index of the pivot. Right? That means that we can now recurse on 2 sublists. I'll go ahead and call Quicksort here recursively, at least how I'm presenting it right now, on the same array, but now instead of L and R, right? L and R, think of it as an array here that continues over here and over here, and then you've got this partition element somewhere in between. It could be equal to L if it was a bad split. It could be equal to R if it was a bad split in the other direction. But let's just go ahead and say that it's P. I want to recurse on everything from L up to P minus 1. And I want to recurse on the right partition, which is P plus 1, all the way up to L, or all the way up to R. So let's go ahead and take care of the left partition first. L doesn't change, but going to the right, it's now P minus 1. And on the right partition, again, the array doesn't change, but you're going from P plus 1 up to R. And that's it. Right? Again, if this if loop is, or if this if condition is not satisfied, that means that they've met in the middle and it's sorted up to that point. Otherwise, they've gone past each other, in which case you don't need to sort it at all. It never executes and it returns from the calling to the calling function. Right? Okay. I want to leave this code up here because I want to go ahead and analyze this with respect to comparisons. Okay. First of all, let's examine this line of code right here. In this partitioning function or method or subroutine or sub-algorithm, if you want to look at it that way, this partition performed a certain number of comparisons, right? It performed a certain number of comparisons. It compared it chose chose the first pivot element, and then it compared it to the next one, compared it to the next one, compared it to move I over. Then J was moved over by making a bunch of comparisons. And the key realization there is that it compared the pivot element to everything in the subpartition here, L up to R, except for, of course, the pivot element itself. So in other words, this function here makes n minus 1 comparisons, right? Because it's taking the pivot element and comparing it to all the other elements. Well, if the size of the array going from L to R, we'll assume that the size here is equal to n, right? Now, in general, the size of the array is n, but don't worry about that. It could be some other n. In fact, I'll give it a capital N over here. We'll focus on lowercase n here being our subarray size. So in other words, going from L to R, there are n elements in that subarray right there, so that we can capture a notion of how many comparisons this entire algorithm does. So there are n minus 1 comparisons. Then we make a call to Quicksort, one recursive algorithm, on an array. Again, ideally, we'll go ahead and assume that it was a roughly even split, because with the size here, we're going to go ahead and assume that it's something like n divided by 2. And the size here, we're going to assume that it gets the other half of them. Now, this is not exact, because in particular, we're ignoring the pivot element, right? If I've got 5 elements and the pivot element is in the middle, then it's not 5 divided by 2. There are 2 elements over here and there are 2 elements over here, and the pivot element gets ignored, right? So it's only going to be roughly n divided by 2. And as we observed before, if it's a bad split, then it's not going to be n divided by 2. It's going to be, say, 0 and n minus 1, right? Everything gets put over into the right partition, nothing gets put into the left partition. That's the worst case scenario, and you can analyze Quicksort with respect to the worst case scenario, but I'm going to go ahead and analyze it under ideal conditions, which is similar to what you would do if it's the average case complexity, okay? So as with a lot of recursive algorithms, to capture the amount of work, you need to set up a recurrence relation, or a recurrence that defines that. So I'll go ahead and do that over here. I'm going to define C sub n to be the number of comparisons by Quicksort on a subarray of size n, right? Remember, we're focusing on the size of the subarray, not the entire array here, okay? Well, we've already analyzed this line, and this line. So let me go ahead and write those down. This line is your non-recursive cost. That's the amount. There's no recursion here at all. This is just another algorithm. This is just another function that you call. So it makes n minus 1 comparisons. Now, how many comparisons are made by this call to Quicksort? It makes a call to Quicksort on the same array, but the size of it is now roughly n divided by 2. We have a function that captures that. The question is, how many comparisons are made by Quicksort on an array, a subarray of size n divided by 2? All we need to do is apply C here, except it's no longer of size n, it's of size n divided by 2. Likewise over here, this is why I wanted to kind of assume that it was an even split, because it makes the analysis much smoother and much easier. That I'm just going to assume that the same thing for the right partition, that it gets roughly n divided by 2 elements, right? Now, simplifying this and collecting all my terms, these are exactly the same. So I make 2 recursive calls to Quicksort on arrays that are roughly half the size. And to do that, I'm making a non-recursive amount of work here, the number of comparisons, of n minus 2. Right? Now, at this point, I'm going to assume that you have the Master Theorem, or that you've seen the Master Theorem, and that we're just, I'm not going to write it down, because I'll go ahead and cover that in class if I haven't. But otherwise, you can notice that this is a recurrence relation. It's a nonlinear, non-homogeneous recurrence relation. And so you could solve this through various techniques, but I don't care really about solving it. I care about getting an asymptotic analysis of it. So I'm going to go ahead and apply the Master Theorem here, and when I do that, this is A. The factor that you're decrementing or decreasing the size of your input is B. And to characterize this function right here, this is order n. In other words, it's order n to the first. And so D is 1. Now, the condition that you need to check for in the Master Theorem is whether or not, what's the relationship between A and B to the D, right? In this case, we've got A is 2, B is 2, and D is 1. So 2, is it greater than, is it less than, or is it equal to? That gives you the 3 cases of the Master Theorem. So we've got 2 versus 2 to the first. They are equal. That implies that C sub n here, the number of comparisons made by Quicksort overall, is going to be order n log n. Remember, there is a d right here, but d is 1, so it disappears. And we get that Quicksort under ideal conditions where it's a roughly even split is going to be an n log n sorting algorithm, which is the best that you can do with respect to comparison-based sorting algorithms asymptotically. Okay?